Hello everyone, today we are implementing Heap class which should support push, pop, top and size operations. So first look at what is heap. Heap is a data structure which keep elements in sorted, and one of the major property of heap is that it is a balanced binary tree, which means the height difference between the left and right subtree should not be greater than 1. So this is the example of Max Heap. If we insert like 8, 6 and 4, let's say, and it is always inserted from left to right manner. For example, if I want to insert 3, or say if I want to insert 3 here, then I want to insert 7, say 7. So 7 would be first inserted here. Then to maintain the heap order, what is the order? That the parent should always be greater than the child nodes. So what would happen? These two nodes would get swapped. So it would become 7 and it would become 6. Then also, to maintain left to right order, if we insert new element, it would be inserted here. Say if we insert 4, say 1, so it would be here, and it is smaller than the parent, so order would not be changed. And let's say if we insert 5 here, then the order, then these two nodes needs to be swapped. So what would happen is, but let's say if I inserted 10 instead of 5, so what would happen then? Then all these three nodes would have to be swapped. So 8 would come here. What was the number again? 5, 4 and 8. Say if I want to insert 10 here, let's keep it this way, and I want to insert 10. So all these 4 nodes would needs to be swapped to maintain the order. So 10 would come up here, and 8 would come up here, 7 would come here, and 3 would come up here. So how to implement this in a class? Let's say. So first, let's declare a class heap, and to store this structure we would use an array. So how the array would work here for us? Let's suppose this is our array, and to maintain one based indexing like 1, 2, 3, 4, 5, 6, 7. So for any particular index, say 2, then it's both of the left and right child would be available at index. Let's say it is marked as I. Then its left child will be available at 2 into ith index, and right child would be available at 2 into I plus 1. So it's both of the child would be available here and here, and for 1 it is 2 and 3. So this is how we can maintain these structure in a array format. So let's declare a constructor, which is ARR, okay, and a default constructor. Make it public. And we want to maintain the one based indexing, that's why we would push here a -1. Okay, so first ARR dot push back. So first operation would be push, let's say. So now we have inserted the new element into the heap. It would need to be maintained. It would need to maintain its priority order. So let's say if we inserted 10, then it needs to be travel, or we can say it needs to satisfy all of this parent nodes. So what we do is, first we would find the index of this current element. So it's one based indexing. The size of the array is itself the index of the pushed element. And what we do here is, while current is greater than 1 and n, ARR of current divided by 2, that means its parent, it's smaller than ARR of current. Then what we do is swap So this is how we maintain our heap data structure. Let's check it's working fine or not. First I would declare a heap max heap, and I would push some element in here like heap dot push. Let's start with 4 and 3, 10, 8, 12 and 5, say 5. Then I would print this heap array to see if it's fine or not. Print for int I equal to 0, I smaller than. So this is our mistake. Like here, it's whether it's one based indexing or not, current would always be -1 from the size. Okay, let's run it again. So we can see the child of 12 are 10 and 5. Let me print index with them also. Cout of I So at index 1 we have 12. So children of 12 are at would be available at 1 into 2 and 1 into 2 plus 1. Children of 12 would be 10 and 5, and children of 10 would be available at 2 into 2 4, 2 into 2 plus 1 8. So 3 and 8 both are smaller than 10, and children of 5 would be 3 into 2 like 6, and 3 into 2 plus 1 at index 7, which is unavailable. So it's working fine. Now we would implement our pop function. Say first implement top, it would be easier. So int top, it would return the root of our tree structure. So return ARR of 1. But if ARR dot size equal to 1, that means our heap is empty. So I would return -1. And again for pop operation. So in our pop operation, what we do is, let's see. So this was our array earlier. Okay, so in a pop operation, our root element would get popped out of the data structure. So what we do is, let's see, make a valid tree first. So this is a valid heap structure. Okay. Both children are smaller than their parents. No. So this is a valid. Okay. Now what we do is, we have to pop 8 out of the heap. Then we can replace 8 with the 4 here. So we replace 4 with the top. Why 4? Because it's the last element in our array, and we will reduce the size of the array by 1. Now we need to maintain our heap priority order. All the roots should be greater than their child. Then we would implement a Heapify function, which would validate our heap structure. So what Heapify would do is, it would swap these two values and bring 5 over here, 4 over here, and 1 would be here. So how would we gonna implement this? Let's see. Then in pop function, what we do is, we will set ARR of 1 equal to ARR dot back, because we just replace our top value with the last element in the array, and I would pop our array. Then our current index ARR dot pop back, and we would initialize a index which would track the element which needs to be put to its correct position. Or here we bring our last element in the array to the top, so we would initialize our current index with 1, and we would run a loop while current is smaller than current. Let's say it's parent. is smaller than ARR dot size. Okay, then its left and right child would have index int left equal to parent into 2 and int right equal to left plus 1. Then if left child is under the range, let's initialize a variable called size. If parent is smaller than child, okay, if left child is smaller than size, and our current parent is smaller than left child, then what we do is we would swap our values, no, not swap, we would store, we will treat the left child as our current parent. Okay, and also if right is smaller than size, means it is under range, and ARR of parent is smaller than, then parent would be equal to right. Let's store the original value. Original parent equal to parent. So if original parent is not equal to parent, that means our value has been altered. Then what we do is we swap the value of ARR of original parent, comma ARR of parent, and I would else break. It's fine. If our parent has not been changed, current node parent has not been changed, that means both of these children are smaller than it. In that case, that will break. Let's see if it's working or not. So this is our heap. This is the generated test case, and we run it. Then first element is 30. Its left and right child are 25 and 5. Left and right children of 25 are 20, 15. Okay. Left and right children of 5 are 6, 5, 2, 5. And left and right children of 20 are 10, and no right children. Then I would do a one pop. Then 30 should be popped out from here. 25, left and right children are 20, 5. For 20, left and right children are 10, 15. For 5, left and right children are these two. Then pop it once again. And left and right children of 20 are 15 and 5. For 15 it is 10, 5. For 5 it is 2. Pop it once again. For 15 it is 10 and 5. For 10 it is 2 and 5. Okay. Pop it one more time. For 10 it is 5 and 5, and for 5 it is 4. So one test case we have, one exception we have to handle, like if to equal to 1. So no elements to pop. So if we pop all the elements, one element is remaining, 2. If we pop all the elements, okay, so it should log